It's now time to learn about the assumptions for regression. The regression that I've been teaching you about is a parametric statistic. It's based on a set of assumptions, as all parametric tests are. And the good news is that the assumptions that you learned for the correlation, for Pearson product moment correlation coefficient, are the same ones as for regression. So there's a lot of overlap. So all the assumptions of correlation apply here to regression. But there are some that I didn't go into a lot of detail about, and I want to do that now. Plus, in regression, you're going to learn 2 additional assumptions that we make for regression. All right, so this assumption is called homoscedasticity. Remember how to say that word? Just break it down. Homo means same, and then scedasticity. Homoscedasticity. Your, high point Scrabble word. All right, so what is the homoscedasticity assumption? It says that the standard deviation of the y values within a given x are the same for all values of x. So let's look at this. If we look at this diagram here, this is showing you homoscedasticity. Why? Well, if we look at this value of x, these are all the y values. Okay, so when x is whatever, 1, when x is 1, here are all the different values of y. These are just numbers, right? So we could calculate the standard deviation of these numbers. And we're just going to let it be represented by SY. All right, so S for standard deviation and Y just to remind us that these are Y values. Okay? Then we move over to the next value for X and we calculate the standard deviation of these numbers. So we get another SY, standard deviation of the Y values. And we do the same thing here for this level of X, for this value, and for this value of X, and for this value of X. So now we have a whole bunch of standard deviations, right? Well, what this assumption of homoscedasticity says is that all of these standard deviations will be equal, homo, same. So they will not necessarily be the same value, because what are the chances of that? But at least these values, these standard deviations will be statistically equal to one another. So statistically, they're all going to be the same. Now, homoscedasticity, you could say, means that the standard deviation of y will be the same for each value of x. You could say it that way. Or you could say, you could square each of these and get variances and say that the variance of y will be the same for each level of x. It means the same thing, because remember, variance is just the squared version of standard deviation. So you can express it either way. So here we see that the dispersion, because remember, variance and standard deviation are just measuring dispersion or scatter. The dispersion or scatter of the y values here is about the same as it is here, and here, and here, and here. So just through a visual inspection of the graph, I can say that, yeah, you know what? Looks like we have homoscedasticity. Now, there is an actual way of testing it, but I don't go into that in this course, just because we have limited time and we are out of time. If we look over here at this diagram, this is showing you heteroscedasticity. So it's no longer same, it's different, hetero. And what it means is that the standard deviation of the y values is not equal across x. Or you could say the variance of the y values is not equal across x. So if we look at x equals 1, 2, 3, 4, and 5, here when x equals 1, we see this much scatter or dispersion. All right, now let's go at x equals 2. We see this much, which is about the same, right? So it's about the same in terms of the degree of scatter. But look what happens when we get to x equals 3. All of a sudden we have an explosion here, looks like, and the scatter is much greater. All right. Over here, well, it's still a little bit larger than it was here and here, but it's about the same. And this level or amount of dispersion is about the same as these two. So if we were to omit this, I would say just looking at these four, okay, this one, skip this one, go here and here, we have homoscedasticity. But then it explodes here, and now that leads me to believe we have heteroscedasticity. Again, there's a way of knowing this with a statistic, but, you know, that'll be something for you to learn in graduate school if you go to graduate school. All right, so we are hoping that we don't have this situation. If we do, what we tend to see is our R value going down. All right, so usually if we violate homoscedasticity, our R will decrease, right? It'll suggest that we have a weaker relationship between X and Y. And the reason this happens is because we're increasing dispersion, right? We're increasing the amount of scatter away from the line. And of course, if our R value goes down, what happens to our predictions? Do they get better or worse? Well, if our R decreases, meaning our relationship is weaker, it means our predictions are going to be not as good, right? Now, here's a little bit of a challenge for you. When might heteroscedasticity increase R? Because I said usually if we violate homoscedasticity, in other words, if we have heteroscedasticity, R will typically go down. When can it, or will it ever go up? Will it ever increase R? And the answer is yes, it could. What if, for example, instead of having an explosion here, what if we had an implosion? And instead of the variability becoming so much greater, it becomes so much smaller. Well, wouldn't that decrease the average distance points R to the line? And if it decreases the average distance points R to the line, it means R will be a higher number. It means that we have a stronger relationship, which means our predictions will be better. All right? So it really depends on whether you see explosions in your data or implosions in your data. Does it matter where the explosion occurs or where the implosion occurs? No, it doesn't. It can happen here in the middle. It can happen at the end. I mean, it really doesn't matter. What matters is whether it's an explosion or an implosion.